Let us start this lecture with a thought process. A man can attain perfection only when undergoing trial and tribulation of life willingly. Most of us, we do not want to have trial and tribulations, and which are very much part of life, and when we will gleefully undergo the transformation during this trial and tribulation, we will definitely get a lot of strength to have perfection in our life, which is the main objective of human life. So, let us recall what we learned in the last lecture. We basically looked at the combustion of solid fuel, and in the process we learned that there are two kinds of regime. One is the kinetically controlled regime of combustion, other is the diffusionally controlled combustion, and today we will be discussing about the diffusional theory of carbon combustion. If we recall that we had discussed about various assumptions what we can make to simplify the problem, and one of them of course is that we are considering carbon combustion, and if you recall that it is one of the simplest one because it is not pyrolyzing fuel. That means the combustion what will be taking place on the surface of the carbon sphere what I have shown here. And unlike in a pyrolyzing fuel in which there will be volumetric devolatilization, here the carbon will be devolatilized on the surface. This is the surface of the carbon itself. Therefore, it is very simpler one to analyze. Beside this, we have assumed that the particle to be spherical in nature. In real situation, it need not to be, and we are considering all other effects along the other direction. If you take a sphere, that we can take a coordinate system of r, theta and phi, and along this theta direction, right, we have neglected the variation of various properties. So, also in the phi, the only along the r direction which I have shown here, like the properties will be varying. And keep in mind that we are considering this sphere basically under a quiescent atmosphere. That means, there is no motion of fluid around it, which is not the case in practical application, unless otherwise you are conducting experiment in laboratory in a very controlled condition or controlled environment, then only it is possible, otherwise it is not. And we are assuming also the steady state burning of the carbon sphere, rather it is quasi steady state as I had mentioned earlier. So, therefore, it is also simplified, and we are considering the diffusional process because we are considering that burning of carbon will be dictated by the amount of oxygen which will be diffusing from the ambient condition, right, toward the carbon surface, right. So, for these purposes what we will do? We will basically invoke the various conservation equation, and first of all we will consider the mass conservation equation. Mass conservation. If you consider mass conservation for one dimensional situation, you will get, of course, under the steady state condition, you will get d by dr rho v r r square is equal to 0. keep in mind that the velocity which the fluid will be or the gas will be going out here with V r. V r is the gas velocity along r direction, and rho is the density of gas. And if I say this is equation 1, if I the equation 1 basically if I integrate, and then you will find that it is basically implies that that is equation 1 I can write down becomes rho V r r square is equal to constant. What is the meaning? If you look at rho V r, this term is nothing but your mass flux term, right. That is mass flux, mass flow rate per unit surface area at various direction, at various location from the center of the sphere. If you see that into the r square, that is area, will be remaining constant, right. So, therefore, it is constant. What is indicating? It indicating that mass flow rate at each r location, it will be remaining constant. However, the mass flux will be inversely proportional to r square. Therefore, mass flux will be changing with respect to r as the radius increases. Therefore, the mass flux will be decreasing. That you should keep in mind. And as I told that oxygen plays a very important role for the combustion of the carbon sphere that we are considering now, as we are only interested in diffusional kind of combustion. So, therefore, we will have to invoke the oxygen conservation equation, right. So, if you consider basically oxidizer species conservation, keep in mind that the momentum equation we are not considering here because of fact that in one dimensional it turns out to be pressure remain constant along the what you call r direction. So, therefore, it is not really required. So, and it is atmospheric combustions that we have already seen for the liquid droplet combustion. So, therefore, we are not considering the momentum conservation equation. However, we will be considering the oxidizer species conservation equation, and considering that no combustion takes place in the gas phase. For no combustion, rather as no combustion is taking place in gas phase, then the species conservation equation turns out to be balance between the convection and diffusion. That is basically m dot double dash r square, this is nothing but your mass flow rate which will remain constant, I can say from the continuity equation. D r is equal to rho d 1 by 2 d by d r r square d y o x by d r. Keep in mind that where y x is the mass fraction of oxidizer and if you look at the D12 is the mass diffusivity between oxidizer and fuel, and of course, density I have already defined, density of the gas, and this region is basically gas region around the sphere. In this equation 2, if you consider that this term is basically due to convection, like and this term is basically diffusion term. You can consider as the mass diffusion term. And as I told earlier that oxidizer species equation basically the balance between the convection and diffusion of the oxidizer, and as there is no chemical reaction takes place in the gas phase. Now, we will consider the energy conservation equation in the similar fashion and similar condition, that is nothing but the balance between the heat conduction and also the heat convection. So, that is the m dot r square C p and d t by d r is equal to k g by d r square d t by d r. Keep in mind that the C p is where C p specific heat and Kg is the thermal conductivity. Of course, T is the gas temperature. And keep in mind the thermodynamic properties are remaining constant along with the radial direction, which is not true, because the C p is a function of temperature, so also the thermal conductivity, but however, for simplicity reason we have kept it constant, and therefore, I have taken out from this differentiation of the first term and so also the second term. So, now what we will do, and this is basically the equation 3. What we will do? We will have to integrate the equation 2 with the following boundary condition. The boundary condition, what we can look at it basically little later on. Let us integrate the equation 2. Integrating equation 2, we can have is basically what we can get is m dot r square. I can take it out because that remain constant. We have seen this is dy o x by dr into dr, and we are integrating between the surface. This is the surface r to r is equal to rho d12. Again I can take out because I am keeping this as a constant, rho d1 to d by dr r square y by x dr into dr. This is at the surface of the carbon to any r. So, I can say this is equation 4. Now, what we will do, we will have to look at apply basically boundary condition for this equation 4. If you look at boundary conditions, and what are that? At r is equal to infinity, that means very far away, this is your r, very far away around infinity, where there is not much changes is occurring. So, what we can say? We can say y o x is equal to y o x infinity, and also the gradient will be 0 if I just plot this from here, the center, and at this point this is basically r by r equal to 0 and this is infinity. If I consider that oxygen level will be basically it is attaining something infinity value is remaining constant as y o x infinity, and this gradient is 0 at this point, like you can say that d y o x by d r is equal to 0. And at r is equal to r, that is at the surface, this is basically at surface of carbon. What we will get? We will get basically mass flux of oxidizer at S is nothing but your diffusivity, and flux y o x dr at, I can say that is the surface, which is nothing but your r is r small r divided by capital R is equal to 1 minus m dot s y o x at surface. Basically, one can say also that this is nothing but your m dot s is equal to m dot carbon at surface, at carbon surface. Basically, I can write down that also. So, this is your constitutive equation, and we can say that this is basically 5, and then this is equation 6. And there is another things we need to look at it. One is the stoichiometric equation, that is F is nothing but your fuel to oxidizer ratio is m s divided by that oxidizer at S. S means at the surface of this carbon, that is S we are using symbol. This is basically S means surface of the carbon. So, therefore, I can write down equation 6 becomes equation 6 S by F is nothing but your 2 d y o x d r surface minus m dot s y o x s. So, I can say this is basically equation 7, and when we will consider this by integrating this equation and substituting that in equation 4. That means, by substituting equation 7 in equation 4, we can get by using equation 7 in equation 4, we can get this way, that is basically m dot r square y o x minus S r square y o x. In the beginning I am not substituting equations, I am just writing so that it will be simplify rho d 1 2 r square d y o x by d r minus rho d 1 2 r square at the surface d y o x by d r at S. So, if you look at this, I can write down that basically I can take this out, basically rho d and then this term, and this term if you recognize that basically nothing but your m dot S by F, these t term together. So, I can write down this m dot r square y o x minus rho d 1 to r square d y o x by d r is equal to basically minus m dot S by F. In other words, I can write down that as rho d 1 to r square d y o x d r minus, I can just rewriting that r square y o x is nothing but your m dot S by F. So, this is we got it, and this I am saying it is equation 8. And keep in mind that this is remaining constant according to continuity equation. Look at this one. This I can write down as m dot r square. Now, if I will do that, then equation 8 becomes and this I can write down due to continuity, which mass flow rate remain constant along the radial direction. So, then I can write down rho d 1 to r square d y o x by d r is equal to basically m dot S r square. I can take it out, there will be some r square here, r square, then what I will get? I will get y o x plus 1 by f. So, this is the equation I am getting, and let me call it as equation 9. Now, what we will do? We will basically integrate again this equation to get an expression for mass fraction of oxidizer. And if we will by integrating nine, we can get x by y o x plus 1 by f equal to S r square rho d 1 by 2 d r by r, and this is we are integrating. So, what we will get? We will get basically ln y x plus 1 by f is equal to minus m dot S r square rho d 1 by 2 1 by r plus c, and this is equation 10. What we need? We will have to apply the boundary condition to for getting this c constant. This is basically a constant. So, by applying B C boundary condition, particularly at r is equal to infinity, we know that y o x is nothing but your y x at infinity. So, if we will do that, what we will get? Equation 10 becomes ln y o x infinity plus 1 by f, because this term will be 0 and when this term will be 0 is equal to r is infinity. So, therefore, this term, if you look at this term, I am just writing for simplicity 1 by r is infinity, this is basically infinity, therefore, this will be 0 is plus c. So, therefore, equation 10 becomes ln y o x plus 1 by f is equal to minus s r square d 1 by 2 1 by r plus ln o x infinity plus 1 by f. So, if we will just take this term to the left hand side, I will get ln y o x plus 1 by f divided by y o x infinity 1 by f is equal to m dot s r square by rho d 1 to 1 by r, and at the surface of fuel, in this case carbon, that is r is equal to r. So, equation 11 becomes I can write down basically, that is r square by rho d 1 2 1 by r, of course, this will be minus, right, and if you consider this as ln, if I can write down just opposite of that. So, that y o x infinity plus 1 by f divided by y o x plus 1 by f, keep in mind that this become plus. So, therefore, this will cancel it out. I can write down this is nothing but your r by rho d 1 2 is equal to ln y o x infinity plus 1 by f divided by y x plus 1 by f. This is your equation 12. So, we now have basically got a relationship between the various terms like mass flux of the which is max relationship between the mass fraction of oxidizer and also the mass flux and diffusivity. In the next lecture, what we will do, we will look at also what happens at the fuel surface, and then we will derive an expression for mass fraction of oxidizer. Now, we will stop over. Thank you very much.